All right, so the bottom of the tower, the bottom of the energy spectrum has to be energy h bar omega times 1/2, with n equal to 0, big N equal to 0, also little n. But let's see if we can see how far we can go in calculating all of the wave functions. Can we calculate the wave functions themselves? Now, you might ask, I can write a Schrodinger equation. I just use for P in the top equation, I use for T, d by dx. For a time-independent Schrodinger equation, the right-hand side is just the energy eigenvalues times psi. Question, is it really true that you can only solve that equation? In fact, we could write down the equation. Let's write down the equation. Time-independent Schrodinger, here it is. Time-independent Schrodinger equation. That's minus d by dx squared for ordinary derivative minus 1/2. The 1/2 is the half in front of the Hamiltonian there. P squared is d second by dx squared psi of x plus the potential energy plus omega squared x squared times psi of x. And if this is the time-independent Schrodinger equation, then what I want to do is solve the equation that this is equal to, let's call it E for the eigenvalue for energy times psi of x. That's the same as writing P squared plus omega squared x squared on a vector is equal to E times that vector. Okay, now, if you know anything about differential equations, you'll know this is a second-order differential equation. You always solve it for any value of the energy here. But what will happen for most values of the energy is the wave function will not go to 0 at infinity. Even worse, it will exponentially explode and get big. It won't be normalizable. It will not have a finite probability under it. There's no way to normalize it. If you try to normalize it, it'll just be 0 because the integral under the square of the wave function will be infinite. To get rid of that infinity, you'll have to divide by it, and the wave function will just be 0 everywhere. So the rule is, one more rule, and we talked about this last quarter or 3 quarters ago or whenever it was, is that what you mean by an honest vector here is one whose square integral, the square of, which is square integrable. Integral psi star psi equals 1. Okay. There are some exceptions to this. For a particle moving on an infinite line, sometimes we introduce momentum states and position states, which are a little weird in this way. But we would like total probability to be finite, certainly not exponentially exploding. So this is one additional restriction, and it's when the wave functions are restricted in this manner, when they really form an honest and good vector space, then that's when the rest of this applies here. It only applies if we're interested in the square integrable wave functions, which we are. And so the point is that when we write down the Schrodinger equation, there are certain definite values of energy which will have square integrable wave functions. Those are the true honest eigenfunctions. If the wave function blows up and goes to infinity, we just throw them away. See, they're not in space. Okay, let's see if we can find psi naught, the ground state wave function. We could write the original Schrodinger equation for it, but we can be smarter than that. Instead of writing h on psi equals e psi, let's write a smarter equation, a simpler equation. Let's use the fact that we know that the annihilation operator, the lowering operator on the ground state, you need to call this psi naught, because naught gives 0. Okay, what is A minus? A minus, A minus is proportional to P minus I omega X. Now, there's some factors in the denominator there, but we don't care about them because we're just going to write that this times psi of X equals 0. And numerical factors like square roots of omega, they don't matter in this equation. Just multiply through by them. And now, remember what P is. P is minus I d by dx. Minus I d by dx minus I omega x times psi of x equals 0. Now we have a much simpler equation than we had before. It doesn't even have any second derivatives in it. It only has first derivatives in it. So we can try to solve it. The trick for solving an equation of motion like this, anybody know what the trick is? There's only a finite number of tricks in solving differential equations. There's a handful of tricks. What's that? No, there's only one variable. What are you going to separate? That's it. Right. Okay. One very standard trick for linear equations like this is to write the wave function as the exponential of something else. Now, this is just a matter of experience. I can't tell you how to guess that.
Yeah, you can guess it because when you multiply through by dx, you get x dx. So the equation comes out as a derivative over right. But it's the form of a logarithm.
Yeah. All right. So this happens to be the kind of equation that you solve. You could solve it in many ways, but one way of solving it is just to write psi of x is equal to e to some f of x, and try to figure out what f of x is. All right, so let's try it. First of all, of course, we can get rid of the i's here. I and I factor out. Furthermore, we can get rid of the minus sign. Both of them have minus signs. And now what's the derivative of psi of x? To calculate the derivative of psi of x, we simply differentiate and we find that, let's call it psi prime, which means the derivative, is equal to f prime, that's the derivative of f, times e to the f of x. To differentiate an exponential, you just differentiate the thing that in the argument of the exponential here, and multiply again by f of x, e to the f of x. Okay, that's psi prime, that's this here, and then we add to that we want to add to that plus omega x psi of x, which means we're going to add to this plus omega x e to the f of x. Now you see what Michael was saying, that the e to the f of x factors out. We can get rid of it. That's why the trick was done in the first place. Let's get rid of all of this here. And our equation is just df dx plus omega x equals 0. That's it. Equals 0. df dx came from here, plus omega x. They both multiplied psi, so we got rid of psi, and that's our equation. This is really easy to solve. A function whose derivative is a linear thing, what kind of function is that? the quadratic thing. So the solution is quite clearly going to be proportional to x squared. In fact, it's going to be f of x is equal to 1/2 omega x squared plus a constant. Let's put the constant in there. Let's put the constant in there. And that's all. Minus. Thank you. Minus 1/2 omega x squared. That tells us that psi of x is equal to e to the minus 1/2 omega x squared. What about the constant? Well, we can add it in, but that just puts a numerical constant in front of the exponential. Since I haven't bothered worrying too much about normalizing it, I'm not going to bother with the constant. The numerical constant out in front is there. It's got an omega, got a 1 over square root of omega in it, but it's not terribly interesting for our purposes. This is psi naught